we are going to study properties of gases and gas laws. Before we start, we need to define what a gas is so that when we are talking about properties of gases and gas laws, we already know what a gas is. However, remember there's this nice guy called matter. Okay. Now, when we talk of matter, matter is a substance that has weight and occupies a space. When we say matter is a substance that has weight and occupies space, by occupying a space or a certain space, it means that matter has volume. However, matter has three states. One is solid, another one is liquid, and interestingly, we have gases. Our topic today is based on gases, and we are going to look at properties of gases. Properties of gases. Properties of gases. Now, the property of a gas is what defines a gas as a state of matter. It is these properties of gases that makes a gas a unique from other states of matter like liquid and solid. One of the property of gas is that if you look at the gas particles, you will realize that these particles are far apart from each other. Okay, so now if we have a volume like this, a container having that volume, you can find one gas particle here, one gas particle there, and another gas particle here. So you can see that the distance between one gas particle to another, the spacing between them is so huge, separating them, making one particle to be so far away from each other. So that is one and the first property of a gas. We look at the spacing of the particles, the molecules in this gas. How far are they from each other? The second property of a gas is easily compressed, easily compressible. Now, we are going to look why is that the gas particles are so easy to compress, unlike solids and liquids. Now, if you look at this distance, we're going to first point. Now, if you look at this distance, let's say molecule A, particle B, and particle C. They are very far from each other, meaning that this is enough space from them. And remember, according to kinetic molecular theory, gases are in chaotic random motion due to an increase in kinetic energy. Now, the intermolecular forces between gas particles are very weak. So the intermolecular force between A and B, between B and C, C and A, those intermolecular forces are very weak, and because of their weakness, if you compress them, and by compressing means that you are applying an external pressure. So if you apply a pressure to gases, they are going to decrease in volume because the pressure that you are applying is overcoming the weak intermolecular forces between these gas particles, and that's the reason why gas particles are so easy to compress. We together. So the third point is that gases have low densities. Now, why are we saying that gases have low density? Let's look at this diagram. So this container, so you can see there's 1, 2, 3, and 4. Because the gas particles are far away from each other, it means that they occupy a large volume. So the volume of the gases are so huge compared to their masses. And because of this, we can then say that the density is mass over volume. We know this. It therefore means that if I increase the volume of a substance, then the density is going to go down. And if it happens that I decrease the volume of a substance, the density is going to go up. In the case of the gases, why they have low density is because that the volume of the gas molecule is so big, meaning that the volume is increased compared to their masses. And if we increase the volume of these gas particles, it means that their density is going to be low. And that is the reason why gases have low densities. So I like putting these points in order because if you can see, the first point, the second point, and the third point somehow depends on the first point. So you must be able to understand and explain the reason why or the reason behind these properties of gases. If we say they have low densities, why are they having low densities? If they are easily compressible, how? You cannot just throw the properties that, you know what, they are easy to compress. You must tell us the reason behind that logic. After knowing this, we can then go straight to gas laws. Now, gases, you find that at moderate situations, they are being affected by 4 variables. One of them is pressure, which is P. We have temperature, T. We have volume, V. And we have finally number of particles, we represent it with N. So it is these 4 variables that normally affect gases at moderate situations. It therefore means that we can write these 4 here and say, so we have pressure, volume, temperature, and number of particles. So it therefore means that I can then take any of these variables, keep them constant, and I check the relationship between the remaining 2 variables. We are saying that it reaches a point whereby we can keep any of the 2 variables constant, any of these 4. If we keep 2 of them constant, then we can check the relationship between the remaining 2 variables to tell us how do they behave. How do gas particles behave if we keep 2 of the 4 variables constant? And by doing that, then it helps us to understand the relationship between gases by just varying these 4 variables when we keep 2 of them constants. For example, we can keep number of moles and temperature constant. These 2 we can say that they are constant, meaning that we are going to vary pressure and volume and pressure. And it is through this that various gas laws were made. And therefore, gas law, when you refer to gas laws, then gas laws tell us the relationship that exists between gas if we vary any of these variables and keep others constant. So gas laws ideally, or gas laws just tell us the relationship which exists between any of these variables when we keep 2 of them constant and we vary the remaining 2. If I keep number of moles and temperature constant, then I'm going to see the relationship which exists between volume and pressure. And that relationship that exists between them is what we call gas laws. And that is how gas laws came up. And we're going to look at those for gas laws. Now, the first gas law that we are going to look is Boyle's law. Boyle's law. Now, I'll write again those 4 variables. You have pressure, temperature, volume, and number of moles. So the first law is Boyle's law. Now, what does Boyle's law say? Boyle's law says that the volume of a gas is inversely proportional to its pressure so long as we keep temperature and number of moles constant. Boyle's law says that volume of a fixed quantity of a gas, is inversely proportional to pressure so long as we keep temperature constant. Now, when we say fixed quantity of gas particles, it just means that n is equal to constant, and therefore we say, according to Boyle's, all Boyle's did is experiment, and he said that, you know what, I want to keep temperature and number of mole constant so that I can see the relationship between volume and pressure. So you can, as a student or as a learner, you can be asked to state Boyle's law. It therefore means that if we increase the volume of a gas particles, then the pressure will go down. Okay, and if we increase the pressure of the gas particles, the volume will go down. So I'll say this is A, and this is A, this is B, and this is B. So it tells us that if we were to just have this, take an example of this. Okay, this is our container. I'll say this is like a piston, so we can push it down. So this is our gas particles, and you can see here the volume occupied by these gas particles in container A is so huge, and therefore here the pressure is very low. So here the volume is I and the pressure is down. Okay, if we look at container B now, we compress this container A to give us container B such that we decrease the volume of the gas particles. Then the gas particles will now be in this case, and this is our piston. So you can see here the volume of the gas particles has gone down. So the volume now has gone down. Why? Because we increase the pressure. So we increase the pressure by compressing the gas particles, and that one is in accordance to Boyle's law, which says the volume of a fixed quantity of a gas is inversely proportional to the pressure so long as temperature and number of moles are kept constant. And therefore we can draw, this is mathematics, so we can represent this in a graph. There are two graphs that we can draw. If we draw a graph of V versus P, okay, then we can have a graph that is like this. Okay. However, if we plot a graph of V versus 1 over P, then we can have a graph with a straight line. So be careful and look at the difference between this. So the one on the right hand side says that volume versus 1 over P, and this is a graph of V volume versus P. Okay, volume versus P. So why are we saying, maybe let's do a small mathematics. If we can have volume and 1 over P here, and we have a table, for example, if you have volume 2, okay, then here let's say our pressure, okay, let's say our pressure is given to be 50, okay, and we have 3. So we can see if the pressure is 50, you can see here the volume is increasing. So we have 2, 3, and then pressure, we expect pressure to decrease, right? So you can have 50, then we can have 40 here. So you can see when the volume is 2, the pressure is 50. When the volume is 3, the pressure is 40. So an increase in volume is decreasing the pressure, and that is what we have here. So if we have a pressure or a volume of 3 here and we have a volume of 2 here, at volume of 3 you can see the pressure is 40, and at a volume of 2 you can see the pressure is 50. So you can see that an increase in volume leads to a decrease in pressure. However, if we were to take 2 and see 1 over 50, if you divide 1 over 50, that's going to be 0.02, and 1 over 40, that's going to be 0.025, and you can see that there's an increase in 1 over p. As the volume increases, there is an increase in 1 over p, and that defines this graph here. So it therefore means that according to Boyle's law, if I plot a graph of v versus 1 over p, we can get a graph of a straight line with a positive slope. So let's look at the second law. And in this diagram, we're just trying to show the effect of pressure, that when increased initial air, you can even see this height. Okay, this height is so huge, I can call it H1, and you can see the volumes of the gas particles very big, or the volume occupied by the gas particles are so huge, meaning that the pressure is low. So when we apply the pressure on the piston, meaning that we are compressing the gases, and you can see now the new volume of the gas particles, H2. So you can see that now H1 is greater than H2, because meaning that V1 was greater than V2, meaning that P1 was less than P1 was less than P2. So in this case now, in this one here, pressure is very high and the volume has gone down. So this is just an illustration to help you understand more about gas law, especially Boyle's law. So now we can go to our second gas law, and that is a guy called Charles' law. Charles, if you are Charles in this class, Charles' law, so we are going to study your law. Charles' law, now we can still write our 4 variables: pressure, volume, temperature, and number of moles. So remember, Boyle's, with him, he varied volume and pressure, and he kept N and T constant. But Charles then, he kept pressure and number of moles constant, and he varied volume and temperature. So Charles then say volume of a fixed quantity of a gas is directly proportional to temperature when pressure is kept constant. Or you can simply say volume of a fixed mass of a gas, or volume of a gas, is directly proportional to temperature when pressure and number of moles are kept constant. And straight we can plot a graph for this volume and pressure, and because it's directly proportional, it means if I increase the volume, the temperature is going to increase, and if I decrease the volume, the temperature is going to decrease. Okay, so it means that in this case we can just have a straight line, and we can define it by saying, oh sorry, this is T, this is T, this is temperature. Okay, you can then define it by say P N is equal to C, or is equal to K. So according to Charles' law, if he varied volume and temperature while keeping pressure and number of moles constant, and he wanted to study the effect, because he realized that, okay, Boyle's only considered volume and pressure. So we can look the third law, and the third law we can call, the third law we are going to look at Gay-Lussac law. We are still going to look at the 4 variables: pressure, volume, temperature, and number of moles. So with Gay-Lussac, with him, remember, Boyle's varied pressure and volume. Charles varied volume and temperature. While now, Gay-Lussac, he came and said, okay, what's going to happen if I vary pressure and temperature? So he said pressure of a fixed quantity of a gas is directly proportional to temperature when volume and number of moles are constant. We can write and say pressure is directly proportional to temperature when V and N is equal to C. By plotting this graphically, we can say that pressure is directly proportional to temperature, meaning that if I were to plot, it's directly proportional in the sense that if the pressure goes up, the temperature also is going to go up, and if the pressure goes down, the temperature goes down. And this is the graphical representation of Gay-Lussac law, and we'll say V N is equal to C. Volume and number of moles equal to constant. And this is all about Gay-Lussac law. Let's look at the third law and the fourth law. And the fourth law, we are looking at a guy called Avogadro's. So this is the fourth law, and we are looking at Avogadro's law. Now we're gonna still write P, V, and T. Remember, everyone, Boyle's law, Boyle's, Charles, and Gay-Lussac, they have varied everything except number of moles. So Avogadro said, look, I'm going to vary volume and number of moles, and this time I'm going to keep pressure and temperature constant. So what did he find? In experiment, Avogadro realized that the volume of a fixed quantity of a gas is directly proportional to the number of moles when pressure and temperature are constant. So say volume is directly proportional to number of moles when pressure and temperature is kept constant, and by that we can have a graphical representation of Avogadro's law by saying volume is directly proportional. So on the x-axis we have our number of moles, and because if volume increases, the number of moles increases, and if the volume goes down, the number of moles also goes down. So it's directly proportional. So it means an increase on the y-axis leads to an increase in the x-axis, and the graph is this, so long as P and T is equal to C. So these are all the laws that we are talking about. Remember, we said gas laws just tell us the relationship between these four variables when we keep two constants and vary other two. And also we look about the four laws. We look at Boyle's law that we said volume of a fixed quantity of a gas is inversely proportional to pressure when temperature is kept constant, and we look Charles' law, which says that volume of a fixed quantity of a gas is directly proportional to temperature when pressure is kept constant, and we look at Gay-Lussac law, which say pressure of a fixed quantity of a gas is directly proportional to temperature when number of moles or volume is kept constant. And for Avogadro's law, it came and said, guys, the volume of a fixed quantity of a gas, or the volume of a gas, is directly proportional to number of moles when pressure and temperature is kept constant. And we have seen the graphical representation of each and every law. As a student or as a learner, you must be able to understand these laws and be able to state them. Not only to state them, but to understand and apply them in mathematical calculations. And also, you must be able to represent them graphically. Now, let's do something very interesting. And I'll do like this. So remember, Boyle's law say, I'll write the first law. Boyle's law say volume is inversely proportional to pressure when number of moles and temperature is equal to C. And Charles' law said volume is directly proportional to temperature when P and N is equal to C. And Gay-Lussac law, which is the third equation, say that pressure is directly proportional to temperature, okay, when V and N is equal to constant. And Avogadro say in the fourth equation that volume is directly proportional to number of moles when P and T are kept constant. So then we can see the relationship between these four laws. If we exclude pressure, because pressure is already in Boyle's law, so we are going to start with Boyle's law. So let me wrap here to create a nice space for us to study. I told you that today we're gonna have an interesting journey, okay? An interesting journey. Magic is happening, okay? So now, if we to start with Boyle's law, we say that V is inversely proportional to pressure, okay? And you can see of all these four laws except Gay-Lussac law, all of them we have volume on the left hand side, okay? So they varied volume with everything. Volume was constant, okay? It's in both. So then, and volume in Charles' law, volume is directly proportional to temperature. Avogadro say volume is directly proportional to number of moles. So if you can see for Boyle's law, you see that volume is inversely proportional to pressure. It means that volume is directly proportional to the numerator and inversely proportional to the denominator, which is pressure. And therefore, if it happens that now we were to include Charles' law, we are going to say we can multiply there by T, so that we can have V is T over P. By saying this, because 1 times T is T, by saying this we are combining Boyle's law and Charles' law, because Boyle's law say volume is inversely proportional to pressure, and it's true. We still have pressure here. And Charles' law say that volume is directly proportional to temperature. We can still look at Avogadro's law, which say that the same volume is directly proportional to number of moles. So we can then multiply by N here, because it's directly proportional to the numerator, and we can say volume is directly proportional to N, T, and inversely proportional to P. So now, having all this is just a combination of all these four laws. Let's look. If the volume is directly proportional to number of moles, that is Avogadro's law. Volume is directly proportional to temperature, that is Charles' law. And the volume is inversely proportional to pressure, and that is that is Boyle's law. So Boyle's law, volume is inversely proportional to pressure, that is Boyle's law. And Charles' law, volume is directly proportional to temperature. Avogadro's law, volume is directly proportional to number of moles. From here, then, we can include a universal gas constant or a proportionality constant R, and then we can write it as V is equal to R N T over P, which we can then say V is equal to N R T over P. And to rearrange this, we can remove P from the denominator, and we can multiply both sides by P. We can multiply both sides by P, and P cancel P, and we can have P V is equal to N RT. So PV is equal to nRT, and this is what we call ideal gas law, okay, or ideal gas equation. So this is what we call ideal gas equation. Okay, so this is how we come to derive ideal gas equation. You can be asked or told that derive an ideal gas equation, or prove that ideal gas equation is equal to PV is equal to nRT. You must be able to combine this and follow until you derive it. I hope you understood how we come up with ideal gas equation. So then, ideal gas equation is an equation of ideal gases or perfect gases. An ideal gas is a gas whose hypothetical, this gas is hypothetical, and its behavior is described by ideal gas equation. Its behavior in terms of pressure, volume, and temperature is described by ideal gas equation. So it means an ideal gas is a gas which obeys an ideal law or ideal gas equation. I hope you guys enjoyed the magic of this, especially deriving gas equation. And having known this, we can then try one or two of the tutorials before we end our class. So this is a tutorial, and this tutorial says in an industrial process, so you can now see where you can apply physical chemistry. Okay, in an industrial process, nitrogen is heated to 500 Kelvin, in a vessel of constant volume. If it enters the vessel at 100 atm and 300 Kelvin, calculate the pressure that it will exert at the working temperature if it behaved as a perfect gas. Now, if something behaved as a perfect gas, it means that that thing follows ideal gas equation. Like I usually say that let's look at the data. Let's write at the data that we have. We are told the nitrogen is heated to. So if it is heated to, it means that T2, that's the final temperature, is going to be 300, or sorry, it's going to be 500 Kelvin. The T2 final temperature is 500 Kelvin. So meaning you started at a certain temperature and you heat it to a final temperature. So this word here is very important because it tells you the final temperature. And we are told in a vessel of constant volume. So the volume is constant, meaning that V1 is equal to V2. If it enters the vessel at 100 atm, if it enters into the vessel at 100 atm, then it means that our P1 is equal to 100 atm. That is pressure. Remember, pressure is measured in atmospheres, and also there are other units, and 300 temperature, 300 Kelvin. So if the gas enters the vessel at 100 atm and 300 Kelvin, so it means that then our T1 here is 300 Kelvin. Calculate the pressure that it will exert at the working temperature. So we have to look for P2 is equal to what? If it behaved as a perfect gas. Now, we were told that the volume is constant, so that V1 is equal to V2, so it won't have any effect. But from here, we can apply a formula that says P1 V1 over T1 is equal to P2 V2 over T2, because the volume is constant. Now, because the volume is constant, we can just cancel the volume because it's not going to have the effect. So then we can say that P1 over T1 is equal to P2 over T2. Just before we proceed, according to Boyle's law, or Boyle's law, Charles' law, Gay-Lussac law, you can see that we are looking at two variables here, pressure and temperature. Now, something very interesting with calculations in physical chemistry is that you can try to predict what you are going to get, so that when you get it, you know that you are right or wrong. So let's look at this. Okay, let's apply this. We have final temperature to be 300 Kelvin and initial temperature is 300 Kelvin. And remember, Gay-Lussac law say pressure is directly proportional to temperature. You remember? So it means if I increase the temperature, the pressure is also increasing, right? Now, our initial pressure is 100 atm and our initial temperature is 300 Kelvin. Our final temperature is 500 Kelvin. So you can see that the temperature moved from 300 Kelvin to 500 Kelvin, and therefore I expect my pressure P2 to be greater than P1, and therefore if I find something less than 100, then I know I am wrong, because this is Gay-Lussac law. It applies Gay-Lussac law. So the pressure increases as the temperature increases. So I'm expecting my P2 to be greater than P1. So from here, we can cross multiply and say that P2 T1 is equal to P1 T2. All right. From here, we can cross multiply and say P2 times T1, which is P2 T1 is equal to P1 T2. And what we are looking for, we are looking for P2. So we can say that we can divide both sides by, we can say that P2 T1 is equal to P1 T2, and you can divide both sides by T1, divide both sides by T1 cancel T1, and you can say P2 is equal to T2 over T1 times P1. And if we substitute, we are going to get 500 Kelvin. So P2 is equal to 500 Kelvin over 300 Kelvin times 100 atm. Okay, Kelvin cancel Kelvin, so whatever you are going to get is in the units of atm, which is true because we are looking for pressure. So here we have 500 and here we have 300, so 0 cancels 0, 3 goes into 3 1, 3 goes into 3 1, 3 goes into 5 1, remaining 2. Okay, in remaining 2, and in 20 it goes 6, which is 18, remainder 2, so it's going to be 6 6 6 recurring. So we have 1.66666 recurring. So we can multiply this by 100 and we get 167 atm. So it therefore means that our P2 is equal to 167 atm, which is the SI unit of unit. Okay, because we have 1 and 2 zeros, so it's going to move it to 2 decimal places, 1 2, and then it's going to be 166.6, which you can round off to 167. So this is how we determine this equation. So now you can see that our P2 is greater than P1, which can make sense because we expected it to go high. The last tutorial that you're looking for is this one. Okay, a 0.5 mole sample of oxygen gas is confined at 0 degrees Celsius in a cylinder with a movable piston. The gas has initial pressure of 1.0 atm. The gas is then compressed, so you compress the gas by the piston so that its final volume is half the initial volume. The final pressure of the gas is 2.2 atm. What is the final temperature of the gas in degrees Celsius? So we know the SI unit of temperature is Kelvin, but then we have been asked to put it in degrees Celsius. So then we can write the data that we have, very important. So we have moles of oxygen, so we're gonna say mole of oxygen is equal to 0.5, and we have initial temperature, or T1, is equal to 0 degrees, so it is 0 plus, we change it into Kelvin, 273.15 Kelvin, and that's going to give us 273.15 Kelvin. What else do we have? We have the initial pressure, so P1 is equal to 1 atm, and P2 is equal to 2.2 atm, and we're told that V1, that V2 here, the gas is then compressed by the piston so that its final volume is half the initial volume. So then if my V1 is V, then V2 is equal to half, initial volume is half V1. So that's the magnitude of our V2. So we can proceed and say we are looking for the final pressure. We're looking for the final temperature. So T2 is equal to what? You can see how you have a lot of data here, and it's very important to write data so that you know what you're working with. So we can look at this and say P1 V1 over T1 is equal to P2 V2 over T2, and in this case we are looking for this guy T2, so we can cross multiply. Let's make it just simple. I just like cross multiplying, so we're going to have P1 V1 T2 is equal to P2 V2 T1, and we're looking for T2, right? So we are looking for T2, and then we are going to divide both sides by P1 V1 P1 V1, so that P1 V1 cancel P1 V1, so that our T2 can be P2 V2 T1 over P1 V1. If we substitute T2, okay, let me just write it here to continue following. T2 is equal to P2 V2 times T1 over P1 V1. So it means that our T2 is going to be, P2 is, we are given to be 2.2, so it's 2.2 atm, times V2. V2 we are told is half V1, so we're going to say 0.5 V1 times T1. T1 we found to be 273.15 Kelvin. Okay, everything over P1 V1, and P1 we're told, remember volume is in liters, but because of this we can just leave it that way. So P1 we're told it is 1, so 1.0 atm, times V1, so V1 is V1 is just V1. So from here atm can cancel atm, V1 can cancel V1, and whatever remains is in Kelvin, and this is 1. So the only thing, because the denominator is 1, so it means that everything is going to be the numerator. So if we multiply that, that is 2.2 times 0.5 times 273.15, it gives us 300, but remember it is in Kelvin, so it gives us 300.46465 Kelvin. But the question says, what is the temperature in degrees Celsius? To move from Kelvin to degrees Celsius, we subtract 273.15. So let me just wrap this part here. Okay, so yeah, I think that space is enough. So now we can move this. We can take this one here and say now T2 is equal to 300.465 minus 273.15, and then from here we can get our answer minus 273.15. that gives us 27. That gives us 27.315 degrees Celsius. But if we check the values that we add, we have two significant figures here. We have 1, we have 2, we have 2. Okay, so we can leave a 1 cent to two significant figures, but you can just put it 27.3 degrees Celsius. So this is our temperature. So I hope you followed. The most important thing is to know the formulas that you are working with and understand the type of data that you have, because as I always say, once you have the data, then you can proceed to look for what you don't have. Okay, so I hope you followed the tutorial and the class. I hope the magic came, you see. So now you may ask yourself that why studying physical chemistry? You as a student, it helps you because you can now see that you are going to apply it in industry. Even in our daily life, we apply physical chemistry. So share the link to your fellow classmates, subscribe, hit the notification bell so that every time we make such nice classes, you get notified, you come and learn. See you in the next class. Thank you.